Hello everyone, my name is Yuan Mu. The paper I present today is PacketGame, multi-stream packet gating for concurrent video inference at scale. First, I will briefly introduce the background. We have been developing a video analytics system at our university for campus security supports, including mobility analysis and anomaly detection. We need to process over 1,000 real-time high-resolution video streams from IP cameras installed in our campus. We use an edge server that has 12 CPUs and a Titan X GPU, and we deployed YOLO-X for object detection with a throughput of 27 FPS. To optimize the efficiency, we apply several existing techniques. The first is TensorRT, a model acceleration tool, and the optimized YOLO-X model can achieve over 750 FPS throughput. Then we apply Infi. It is a frame filtering approach proposed in our last year MobiCom paper. Infi selectively passes necessary frames to the inference module, thus can further improve the efficiency. Notice that the throughput tests are all started from the video frames. However, when we move to the real system that starts from the encoded video streams, we found that the end-to-end concurrency is bottlenecked by the decoder. The reason is clear. The decoder needs to process all the frames, while the inference model only needs to process selected frames passed by the Infi. So, in this work, we propose a new idea to improve the concurrency level of video analytics, that is, to selectively pass video packets to the decoder, and we call it packet gating. Compared with existing ideas, packet gating is the first that can reduce both the decoder and the inference overheads while supporting commodity cameras and offline videos. Now I will introduce the design of our packet gating solution. To selectively pass packets to the decoder, we need some quantitative scores for video packets from concurrent streams. The first available hint is the historical feedback. Here, following previous frame filtering methods, we use the redundancy feedback that checks whether the new inference result is identical to the latest result. Then we formulate this task as a multi-armed bandit, MAB, where each stream represents an arm. Once some streams are selected, these arms are played. Then we can receive the corresponding rewards, 1 for necessary inference and 0 for redundant inference. It is an exploration and exploitation process. Then we can use received historical rewards to compute the packet scores, and we named this module as the temporal estimator. Besides the historical feedback, the packet level metadata is also an available hint, and we choose to use the packet size and picture type metadata, which can be directly read by the parser without any decoding operation. We divide packet metadata into two views according to the picture type, either independent or predicted frames. Then we use the sequence of packet sizes in a time window as the inputs and design a neural network-based predictor. To train the predictor, we need to offline collect pairs of packet metadata and the corresponding redundancy level. Now we have packet scores returned by two modules, one from the contextual predictor and another from the temporal estimator. So it is natural to study how to fuse them. We propose to fuse the temporal estimator's output just as another input view of the neural network. Before the fusion, there are two input views. And now we add the third view and concatenate the score before the last dense layer in the neural network. Now we have obtained quantitative scores for these packets, and we need to do the cross-stream packet selection. We formulate it as a combinatorial optimization problem. Given the scores and the decoding costs of packets, we aim to maximize the summed scores of selected packets under a decoding budget. Since the packet decoding costs are dynamic, which depends on the picture types and the codec configurations, solving this problem is non-trivial. Fortunately, we show that this problem can be seen as an approximately fractional knapsack problem, and we prove the approximation ratio of the greedy algorithm. In practice, such a ratio can bring more than 95% performance guarantee. Combining all the three modules, we present the PacketGame solution, and we prove an overall performance guarantee using the contextual MAB framework. Now it's time to evaluate our PacketGame. We use 2 public datasets and 1 dataset collected from our campus IP cameras. These datasets cover 3 types of video sources, that is, IP camera, offline videos, and mobile cameras. And we consider 4 video inference tasks, including person counting, anomaly detection, super resolution, and fire detection. PacketGame's code is open sourced. First, for the overall performance, we set the target accuracy as 90%. On the 4 tasks, PacketGame achieves 2.1 to 4.8 times end-to-end concurrency compared with the original pipeline. And we did ablation study and found that contributions of contextual predictor and temporal estimator varies in different tasks. For example, the contextual predictor outperforms the temporal estimator for the person counting task, while for the super resolution task, the temporal estimator dominates the contribution of the performance. We also tested several micro benchmarks, and PacketGame shows robust effectiveness with respect to involved variables, including the training size, the window length, video codecs, and so on. If you are interested in details about our design, theoretical analysis, experiments, please read our paper. Well, here are some take-home messages. First, the system bottleneck for multi-module pipeline is constantly changing, and now it is the decoder's turn for the large-scale video analytics. Packet gating is promising and easy to implement. Please try PacketGame for your video analytics system. And the third is, in the future, similar ideas could be explored for packet-level selection of other modalities like the audio and motion signals, and we hope to inspire your research. Last but not least, I really need to thank my advisors, Professor Xianyang Li and Professor Lan Zhang, for their support and guidance. And I want to thank researchers and the engineers at IAI for developing our video analytics system at USTC. Thanks for your listening. Please feel free to contact us if you have any question.